Hello, linear algebra student. This video is for chapter 1.9, part 3. So we talk about onto and one-to-one definition of transformation. Now we're going to introduce two new theorem 11 and 12, that talks about if the mapping is a linear transformation, like the last example that we works on, then we can use some theorem that we have discovered for solving equation to help us to define if something is one-to-one or onto. So for one-to-one first. So for one-to-one, remember we discover if it is one-to-one by thinking, can I find AX equal to B for all B have to have one unique solution, right? So only one X that come to it. So what happens is if it is one-to-one, then the theorem say T of X must be 0, has only trivial solution. That means for only one of them, which is 0. This one has to have one solution, and this is easy to see, right? Because for it to have trivial solution, so you just have to make sure that all the you don't have any free variable, right? So this is the proof. So this theorem is a if and only if. So you have to prove this one-to-one and have this. And then if you have T of X equal to 0 has one solution, then it is one-to-one. So let's say the first direction is one-to-one first. And then it becomes T of X equal to 0, only one solution, only trivial solution. Only if it is a linear combination. And then the other way around is, so this is the A part. B part, we need to say, show that T of X equal to 0 have only one solution, then it is one-to-one, right? So the first is this A part, and then this is the B part. Since T is a linear transformation, and then T of 0 equal to 0, so for linear transformation, T of 0 must equal to 0. So, and because it's one-to-one, so it has only one solution, and this is the solution. So T of X has only the trivial solution, okay, because it is one-to-one. The second one is the other way around. So if I know that T of X equal to 0, and then we have to prove that it is a one-to-one. To prove that it is a one-to-one, we assume that it is not one-to-one first, and then to prove the contradiction. So we assume that it is not one-to-one, so there's two vectors that go to B. But because of linear transformation, see how, because this is linear transformation, so T of U minus B is equal to 0. And if you find T of X equal to 0, and this will contradict the assumption, right? Because this is the only way to, and so this must be one-to-one. So so this is very important. If you want to prove one-to-one, you just have to check T of X equal to 0 has the only trivial solution, okay, which is looking at the if there's any free column for solving the A and then 0, 0 solution. So basically you just need to check RREF, A and then 0. So make sure that there is only no free variable, right? Only one solution. So this would, if this works, then it is 1-to-1. So that's theorem 11. How about theorem 12? And also, okay, what theorem 12 said two things. So if it's a linear transformation, then onto also implies that the columns span Rm. So you have a lot of columns in A, and actually those a linear combination of those things span the whole Rm. The second, if it is one-to-one, then the column A is a linear independent. So this is, which is actually the same as this. If the columns are linear independent, so when you solve them, they have no free variable. So, but this is useful because one-to-one, well, linear independent is easy to check if there's only two, right? So those things are easy to do. So let's so these are the proof. So if T is onto, then AX equal to B must have at least one X for all the B. That means A of X is always consistent. And so there must, for all B, there must be a combination. So that means column A span IRM. So all those the x are the weights, right? So when you multiply A x, that is using those column V1, V2, X1, X2, they would equal to B, must have a solution. Okay, and if A span Rm, that means A of x has solution for each one of them. So that means T is on 2. So that is the other way around. What about the 1-to-1? So 1-to-1 say that Ax equal to 0 has only trivial solution from theorem 11. And by definition of linear independence, do you still remember linear independence definition? That means when you're combining all those linear combination, they are equal to 0, and that's the only trivial solution. So this is just say by definition. And then if they are linear independent, then Ax equal to 0 has only the trivial solution. So some using theorem 11, that means it's 1-to-1. Okay. So let's do a lot of this linear dependent proof. So we have a linear transformation. Go like this. We know it is a linear transformation because I can write it as a standard matrix. So what is a standard matrix? So let me write it down as like a column vector, x1, x2. After you do that, then it becomes 3x1 plus x2, 5x1 plus 7x2, kind of like the equation, systems equation, and then x1 plus 3x2. So you can see that you can factor the x1 out. So the standard matrix will be all this coefficient of x1 as 1, 3, 5, 1. That's what you do, like I think in like 1 point something, 1.3 or something, or 1.4. Don't know if 1.3 or 1.4. And also, okay, so no. And then so this is column 1, and then the second column is the x2, like 173. Yeah. And then what do we map from what to what? So I have two weights. So this is x1 and x2. So my A would be 2. And then these are vertical columns are dimension 3. So B is 3. And is this a particular transformation 1-to-1 linear transformation? 1-to-1, according to theorem 12, meaning if it's 1-to-1, then the columns are independent, right? Are they linear independent? So we have only 2 columns and 2 vectors, so 2 columns. They are not multiples of each other. So they must be independent, right? So must be independent. And if they are independent, then according to theorem 12, it is 1-to-1. Theorem 12 is 1-to-1. So for every B, you can only have one way of making it from there. Is it an onto? Let's look at theorem 12. Theorem 12 is onto if the whole thing spans it. How do I know the whole thing spans it? Remember, we would just do the onto. Oh, no, this is 1-to-1. Onto is yeah. Onto is the number of if does every row has a prefix position, right? So of course we only have 2 columns. So let's do row reduce A 3 5 1 1 7 3, and we can do row reduce A. It become we only have 2 prefix row, so not every single one. So no, not on 2 because 1 0 0 1 0 0, we only have 2 prefix column, a prefix row, right? So not all of them. So it's not on 2. On 2 means every single one of them can be manufactured. And as a matter of fact, you only have 2 columns. How can you manufacture in R3? So it's not possible. The second one, we have this. So write the standard matrix. So write it out as x1, x2, x3 maps into 0, x1 minus x2, x2 minus x3. So we can write A would equal to where are all the x1? First one doesn't have. The second has a 1. The third doesn't have x1. The second, no x2. This one has a negative 1 x2, and this one has a 1 x2 for the last one. x3, nothing, nothing, and then negative 1. So that is our standard matrix, right? Is it 1 to 1? To see 1 to 1, we would have to check if I can solve ax equal to 0, right? If it is one solution, only trivial solution. Or I have to say if they are linear independent, right? So it's possible. So we just have to do a reduce row echelon 0, 1, 0. Did I 0, 1, 0, 0, negative 1, 1, 0, 0. Oh, it is. Do I have a 3? Oh, yeah, it's actually 3x3. So this should be a 3, negative 3. So I do a reduce row echelon for B, and I have two prefix column only, right? So it is so if I just actually 1 to 1 means a of x equal to 0, right? So if I do it, so there's actually more than one solution, right? Only REF have 1, 0, negative 3. I should actually do the 0 because this side should be 0. 0, 1, 3, 0, 0, 0, 0, 0. So this is only, so there's a free variable, right? So it's not 1 to 1. One free variable. So not 1 to 1. Is it on to? On to means if I can actually do R3. No, is it R3? Yeah, can I do R3 from them? So if I do the row echelon of 0, 1, 0, 0, negative 1, 0, 0, negative 3, it seems like they are not, right? So because there's some B that is not possible. So this is also no because I only have two. On two is 1 to 1. Yeah, so look at 1 to 1 on to if it A span Rm. Does it span it? Does it span it? That means can I have all Ax equal to B has solution? Ax equal to B, does it have solution? Let's look at 11. On to say, look at 11 is this. Oh no, 11 is 1 to 1. On to means the A has to span R3. Does it span it? So when I reduce it, so it is 1, 0, negative 3, 0, 0, 0, 1, 3, 0, 0, 0, 0. So x like so this is like that. So if it spans it, so let's look at theorem 4. Theorem 4, long time. So theorem 4, if it spans it, so Ax equal to B has a solution. A has a prefix position every row, so but I don't have a prefix position in every row. So for on to, you look at prefix position in every row, right? Right. So not prefix position in every row. So for on to, you look at the row. For the 1 to 1, you look at the column. There is one free column. Okay, so last one. Do I have enough time? I think I will do